All right, a quick talk through of Unit 9 test review. I've gone through and solved everything out, and I just want to talk about kind of how we set each of these up, especially looking over the homeworks and some mistakes that were made, maybe clarifying those things as we look at this review together. So, number one, find the amount of an investment of $5,000. Find the amount an investment of $5,000 will grow to with 4% interest compounded monthly for 8 years. So we are going to be using our compound interest formula, which you see I'm highlighting over here, boxing over here. So the amount equals the principal. We've been given that principal of 5,000 times 1 plus the rate as a decimal. So we've been given a 4% interest rate, but we need to use that as a decimal, which is 0.04. And that's compounded monthly, so that's our n. The number of times that it compounds is n. So if it's compounding monthly, that's going to be 12 times per year. So our n is 12 compounded monthly. That's 12 times per year. And then the time, t, is for 8 years. So for 8 years, we have 8 years there. Okay? And then all we really have to do once we set up our equation is start solving it out. So the first thing I did 0.04 divided by 12. And then I added that to 1. That's how I got 1.00333. I also did 12 times 8, which gives us 96. Order of operations, we're going to take 1.0333 to the 96th power, and then multiply that number with 5,000 to get our amount. And then we are dealing with money, so we are rounding to the second decimal place, or to the hundredths here. Okay, number 2. This we are comparing if it is better to go with compounded monthly at 1.1% or compounded quarterly at 1.3%. So we're going to be using the same principle. So I'll highlight that in blue. That's our principal. So we have that same number there. And then our rate, we have the same time, so it's 5 years. So that's where I got that 5 from on each of these. Let's see. And then in our first equation, in green here, 1.1%, so there's my rate as a decimal, 0.011, compounded monthly, so that's 12 times it compounds. So let's see, compounded monthly, that's where I get that orange number. So that's my first equation set up. And my second one, or 1.3%, so as a decimal, that's 0.013. Compounded quarterly. So when we're talking about compounded quarterly, that's 4 times a year. So I'm using 4 there. Okay? And then we follow the same kind of process, order of operations. I did inside my parentheses. I did division here and then added it to 1. I was also able to multiply these to get 60. So 1.0009 to the 60th power. When I raised that, this was kind of my rounded decimal there. And then I multiplied that with 3,000 to get this value. In my other one, same idea, follow that same process, and I get this value here, $3,201.14. Over here I have $3,169.54. So which one made more money is really what it's asking. Yields the greater return, and that's going to be our 1.3% compounded quarterly. All right, number 3, we're using half-life. And so essentially what I did in this side of work over here, I needed to figure out my rate. So this is our formula, right? Amount equals original amount times E, raised to the rate times time power. So we had information about, again, for half-life, we're using half of that life, which ends up giving us 0.5 equals e to the k times t. And that's one of the formulas that we were given in the notes. So if you don't remember that, you can take the original value, and then we're using half of that. It's always going to bring you here. Of course, we're working with the time of 8 days. So it's raised to the k times 8th. And so essentially we're solving for k. I natural log both sides. So ln times 0.5 equals, well, natural log canceled out with e. So I have k times 8 here, and I was able to divide 8 to both sides to find that k is equal to negative 0.08664. That's our rate. Now that we know that, we can go in and plug in the information to solve for 32 days. So again, same formula, but now we have our information here. So when we do that, I just kind of punched it in the calculator in order, and then it wants to round to the nearest tenth of a gram. So that would be 12.5 grams. Okay, number 4, we're finding the inverse. So remember the steps for finding the inverse, and I kind of skipped a step when I wrote it down because this f of x is really our y value. So we rewrite it so that that's y. And then when we inverse, we just switch out our x and y. So I took this x and wrote it, or I replaced y with x here, I replaced x with y there, and then we're solving. So essentially what I need to do is I need to get this log 5 times y plus 1 by itself. So I add 2 to both sides first, gives me x plus 2, and then I divide 3 from both sides. And that gives me x plus 2 divided by 3. Now in order to get rid of this log 5, we're going to exponentiate. So I give a 5 on this side, and that cancels that out to just give me y plus 1. On this side, when I exponentiate, I'm getting 5 raised to the x plus 2 over 3 power. Once I've done that, then in order to get y by itself, I'm subtracting 1 from both sides so that our final answer, well, we get y equals 5 to the x plus 2 over 3 power minus 1. And then we write it as an inverse. The inverse of x equals 5 to the x plus 2 over 3 power minus 1. So that's finding the inverse on 4. For number 5, same process. We're replacing this with y, and then we're switching our x and y values. So x and y are now over here. We need to get this by itself. So I subtract 7 to both sides first. It gives me x minus 7 equals 3 times y plus 4 to the 3rd power. Then I'm dividing this 3 out. Again, I'm trying to get this piece by itself. So I'm dividing 3 to both sides. I get x minus 7 over 3. I tried to color coordinate here in black. This is my, my equation after I do that work. And then in order to get rid of the 3rd power, I took the cube root of both sides. So those canceled out. And I was left with, I flipped my equation around because I like having my y on the left side. So y plus 4 equals the cube root of x minus 7 over 3. Then I was able to subtract 4 to both sides, and then we have to rewrite it. So the inverse is cube root of x minus 7 over 3 minus 4. All right. To find these compound guys, we're going to take g of x and insert it into our f of x. So I'm taking g of x, which is x squared minus 2x plus 6, and I'm replacing it for x in my f of x function. So I'm taking my yellow function and I'm replacing it for x here. So I have 3 times, so 3 and then times whatever my g of x function was, in this case x squared minus 2x plus 6, and then I'm finishing this out minus 4. So I just replaced x with that function. Then I'm going to evaluate, so I distributed my 3 into all 3 of those terms to get this, and then I'm combining like terms to land so that f of g of x equals 3x squared minus 6x plus 14. In number 7, we're doing it the other way around. So we're finding f of x, or g of f of x. So I'm taking my f of x value and plugging it into my g, my function for g. So instead of, and I guess I'll just highlight this in red, everywhere in our g of x function that we see in x, we are going to replace it with 3x minus 4. So 3x minus 4 squared minus 2 times 3x minus 4 plus 6. If you see my work over here, I just worked out 3x minus 4 squared is not 9x squared minus 16 or plus 16. You can't just take that square and give it there. It means there are 2 sets of these multiplying. So you've got to multiply them out and then combine your like terms. I like to use FOIL. You can do the box or whatever. So once I have that, that was what I got here in blue. In red was when I took negative 2 and distributed it. So negative 2 times 3x, negative 6x, negative 2 times negative 4, positive 8, and then plus 6. This guy's just hanging out. We combine like terms so that g of f of x equals 9x squared minus 30x plus 30. Okay? And then our f of x and g of x inverses. No, because f of g of x did not equal x. So when we did f of g of x, which we did just up here, we did not get this to just equal an x. And same thing over here. When we did g of f of x, it did not equal x. So we already did the work to find f of g of x. So I just used this value here, and I just plugged in a negative 2. The other way that you could do this is you could take g of negative 2, get that value, and then plug it in for your f of x. You would also end up with 38 there. Same thing for g of f of 1. Well, I already figured out g of f of x, so I just took 1 and plugged it in and got out a 9. If you did f of 1 and then took that answer and plugged it in for your g of x, that would also work. Okay, numbers 10, 11, and 12. These are fairly simple, but they can be confusing. So we're always looking at the inside here. G of negative 1 means I'm looking at my g of negative 1, which is 0. So g of negative 1 is 0, so I'm replacing that here. to find f of 0. So when I go to my f of x graph here, I'm going to 0 on my x-axis, and the corresponding is 2 on the y. So when we use 0 here, it corresponds with 2. Same thing for 11. So if we're finding f of 2 first, so I'm going to go 1, 2. And then the corresponding point there is 1, 2, 3, 4. So when my f of 2 is my input, 4 is my output. And then I'm taking that and I'm giving it in the g. So g of 4. So I'm going to go to my g of x chart. I'm finding 4, and it corresponds with 2 here. So g of 4 is 2. And then finally, g of 1. So I'm going to my graph here for g, or my chart. G of 1 is 1. So I'm replacing that here. G of 1 is actually 1. So that means f of 1. And if I go to my chart here, f of 1, so I'm going to go 1 on the x, which means 1, 2, 3 on my y. So f of 1 is 3. Okay, last few graphing things. So for this one, our 2 natural log times 1/2 of x plus 1. We're going to do our parent and then transform that into our x of e to the y. And this is that table that we have here. And then we're looking, anything inside here with the x in the parentheses is happening to our x value. Anything on the outside is happening to our y. So I have 2 and 1, so 2y plus 1, and 1/2 of x. So 1/2 of 0.1 was 0.05, 1/2 of 0.4 was 2, 1/2 of 1 was 0.5, 1/2 of 2.7 was 1.35, and 1/2 of 7.4 is 3.7. And then when I did 2y plus 1 right, I'm doing 2 times -2, which is -4, plus 1, -3, and so on and so forth. And then we just plot those. Okay? And so as I plot these points, our asymptote is going to be x equals 0. Our domain, which is how far left can we go? Well, we can go -0. And how far right can we go? To infinity. And then our range. How far down can we go? Oh, negative infinity. How far up can we go? Positive infinity. Okay, so for this one, we're doing our parent graph is y equals e to the x. And this is that standard kind of table that we use with e to the x. And then this negative, and I saw this on some homeworks, be careful that you don't apply the negative here in your parent graph. It needs to be applied in your second part here. So this negative is affecting our x value, so the opposite. And then -1 is going to be going over here. So we have -2 and and 0.1. So all this stuff doesn't really, sorry, this is pretty standard. And then we're looking at it over here. So -2 and the opposite of that, +2. -1, the opposite of -1, +1. 0 stays, opposite of 1, -1, opposite of 2, -2. And then we're subtracting 1 from our y value. So 0.1 minus 1, -0.9. 0.4 minus 1, -0.6. 1 minus 1, 0. 2.7 minus 1, 1.7, and 7.4 minus 1, 6.4. When we plot those, we get a graph like this. Our asymptote is negative 1, and our domain is, we can go left to infinity, we can go right to infinity, so negative infinity, positive infinity. Our range, we can only go down to negative 1. We can go up for infinity. All right, and then the last few. So for this one, our standard is, our apparent is y to the log base 3 to the x, or x. And then if we rewrite that, we have 3y equals x. So 3 to the y equals x. Y is our exponent here, so this is where our graphs are kind of like flipped. So I'm using negative 2, negative 1, 0, 1, and 2. And when I input y to the negative second power, I get 1 over 9. I'm sorry, 3 to the negative second, 1 over 9. 3 to the negative first power, 1 over 3, so on and so forth. And then we're looking here. Out front, I have a negative, so that's going to be affecting this y. Outside, I have a plus 1 that's affecting here. When I look inside, we use the opposite of what's inside here, so this is going to be x minus 4. And then we're taking each value, and it's being affected by that transformation. So 9 minus 4, 5. 3 minus 4, negative 1. In the same way, we take this value and then input it here. So negative 2, the opposite of negative 2 is positive 2, plus 1, 3, so on and so forth. We'll plot those points. And for this, our asymptote is going to be negative 4. X equals negative 4. Which means our domain, we can only go as far to the left as negative 4. Or we'll always be approaching it and never actually cross it. We'll just get closer and closer. And then we can go to the right, we can go positive infinity. For our range, we can go up for infinity, and we can go down for infinity. So negative infinity, positive infinity. Number 16, our parent graph here is y equals 2 to the x. You have to be careful, don't include that negative here. I saw some of that on the homework. This is a transformation. It's going to be worked out over here. So our parent graph. So if x is negative 2, if it's negative 1, if it's 0, if it's 1, if it's 2, what does that change our y to be, or what does that work out to be? So you work that out on the table. Then over here we have our transformations. We're doing x minus 3, so we're doing the opposite of that. We're doing x plus 3. And then we have a negative out front and a positive 2 at the end there. So this is a reflection, right, or a flip kind of thing. So a negative here and a 2 here. So I've got negative 2 plus 3, 1. Negative 1 plus 3, 2, 0 plus 3, 3, 1 plus 3, 4, 2 plus 3, 5. And then I'm doing 1/4. The opposite of that is negative 1/4 plus 2. And so I'm working those pieces out here. Negative 1 plus 2, 1. Negative 2 plus 2, 0. Okay, once I have that built out, then I plot my points. Our asymptote here is y equals positive 2. So our line's always going to be fractionally just approaching that asymptote without ever actually touching it. It'll just get smaller and smaller and smaller, closer and closer. And our domain, we can go negative infinity to positive infinity. No restrictions there. My range, we can go down. So we can go negative infinity down. We can only go up to approaching 2 without ever actually crossing it. So only approaching 2 on our range. All right, and then our last one. Our parent function, y equals 3 to the x power. So I'm solving for x, so that means I'm using, not solving for, but my exponent is my x values, so that's going in on this side, our 5 favorite numbers. And then when we plug those in, this is what we get out. And then we're looking at how are those things affected. So in my exponent, I have x minus 1, and that minus 1, then we're doing the opposite. We're doing x plus 1 here. Affecting my y value on the transformation is this 1/2 out front. There's nothing adding, subtracting out here, so there's nothing changing it there. So this is just 1/2 times our y value. So -2 plus 1, -1. -1 plus 1, 0. So everything for my x is being filtered through this. And then everything for my y. So 1/2 of 1/9. 1/2 times 1/9 gives us 1/18. 1/3 times 1/2, 1/6. Okay, and then for these ones, I wrote them as mixed numbers because it was easier for me to graph seeing them like this. Okay, I can go 1 and then 1/2. I can go 4 and then 1/2. So they're graphed over here. Our asymptote is going to be 0. And then our domain, we can go, I guess I don't have my asymptote written in there. Oops. So y equals 0. Our domain, we can go left for infinity. We can go right for infinity. So we can go negative infinity to positive infinity. We can go down, so our range, we can go down only to 0. We can go up for infinity, so 0 to infinity. Okay. If I made any mistakes on that, I do apologize. I did part of this out in the real world, waiting for an appointment. So I was a little bit distracted when I solved this out, but hopefully it made sense. If you have questions, please be sure to ask them so that you can get clarification on these things. All right, I hope you're all doing well, and we'll be seeing you soon, hopefully.